Hi guys, well welcome back. This is 4I. We're going to work on the chain rule, which is essentially differentiating functions of functions. Let's have a little look down in the book to see how they write this one. It's just the rule which they give us. And here we go, here's the rule. Let's make it big here. We've got dy dx is equal to dy du times by du dx. That's the rule which you're going to be using where we've got this function of y, but which is a function of another function, u. So we'll say, let's do dy du, and then times that by du dx. And we'll do a little proof for this one as well. Now, there's another way of writing this, another definition for the chain rule is writing it as a function of a function in terms of f and g. To be honest, I like the fractions version of this more. That's kind of quicker and easier to use from my perspective. It's just the other version is just, if you have it in functions notation, you might wish to use that. But I see that as less clear, but we'll discuss that as we go through. Okay, so well, let's just show to start off with that when we take a function, let's take this one, 3x minus 1 squared. Let's just show what the derivative of this is. So let's do 3x minus 1 squared, that's y. Now, up until now, we'd need to play around with this and get distinct terms which are powers of x, which are multiples of powers of x. And so we get 9x squared minus 6x there plus 1 when we're multiplying out this double set of brackets. And that's not differentiating it just yet. But at this point, we'd need to differentiate it so we could, well, be a bit cheeky to write down f, y dash, perhaps you do that with f. We're going to write dy dx, that's our gradient function. And you know what the rule is, times by 2, use the power by 1. There we go, we've got 18x, we've got minus 6. Okay, well, when you're looking at this original function, you might have thought, well, why can't I just use my power rule anyway? I could say, dy dx is equal to 2 lots of this thing, 2 lots of 3x minus 1, and I'll reduce my power by 1. Well, we've only shown so far that you can differentiate individual terms and terms which are in the form of ax to the power of n. Okay, so we don't know how to do this. We haven't seen this format so far. However, the chain rule allows us to do it because here we can see we've got a function inside a function. Now, what's missing here compared to this? Well, let's multiply this out and see what we're missing. We've got 6x minus 2 there. You can see that we're missing an extra times by 3. Now, where would that times by 3 come from? It comes from the derivative of what's inside. So if you times this by 3, you end up getting the right answer. Okay, so let's actually use, before we prove the chain rule, let's actually use it then and see how it's working. Y is equal to 3, let's go back, 3x minus 1 squared. How would we use this? Well, we'd say u is equal to 3x minus 1. Now we'd work out du dx is equal to 3. And dy du, oh, hang on a second, this isn't in terms of u. So we're going to need to make y in terms of u. And so now, seeing as the function inside is what we're saying is u, we can say y is equal to u squared. Now we can work out dy du. Okay, du, that's equal to 2u. And now we can say dy dx, which is what we're looking for, because u is just complete construct, right? We're almost like a dummy variable, if you like. It's just something that we are making up in order to answer this question. So dy dx is what we're interested in. We don't care about u's. The question wasn't in terms of u. We want to find this derivative with respect to x. We want to ddx it. Okay, and so that's going to equal to dy and dx. We'll split that up like their fractions and do times by u and times by du there. So du on the denominator and the numerator there. You can see that those sort of cancel. Well, we can't actually cancel them though, because these are not fractions. These are our definitions for our derivatives. So this is not really a fraction, but it does come from fractions. It comes from the delta y over delta x. But when the limit of delta x tends to 0, or remember, we've been using h there for delta x, our small change in x, and we've been using a function f of x plus h minus f of x there for delta y. That's delta y is just a small change in y as you go from one point, or xy coordinate point, to your next coordinate point, and you're bringing those points together. So we're going delta x along and delta y up. So that's where these things are coming from. But this is just a definition, so it's not a fraction. So we can't really cancel the du and the du, and we can, this is the rule. Now, we're just going to use the rule at the moment, and then we'll prove it in a bit. Okay, so if we substitute in here, we're going to put the 3 in here. Okay, and then the dy du is equal to 2u there. We can see the u's essentially cancel, but they're not really cancelling, to leave us with dy dx. Now this is our answer. We just need to substitute back in what u is. Now what was u? U was defined to be 3x minus 1 at the top. So we're saying 2 lots of 3x minus 1 and times by 3, which is exactly the same as what we were thinking of before when we did this the first 2 times. So there we go. We're getting an answer of now 18x minus 6. And we are done. That's our derivative. Okay, so that's the mechanics of this. And as I said before, there's also the other way of writing this in terms of functions notation. I'm not going to do this at the moment, but I'm going to have a very quick look at the proof. And the proof is just pretty straightforward, to be honest. It's saying, well, let's do it in terms of y and u. Let's say y, instead of saying y is a function of x, let's say that y is defined to be a function of u of x. So there's a function inside of y. Like, for example, when we were saying 3x minus 1, okay, we would be defining y of u be equal to u squared. Okay, just forgetting about the x for a moment, and then u of x would be 3x minus 1. Okay, so that's how we're setting up this definition in order to lead to our 2 fractions. Okay, so y is a function of u, and in turn, u is a function of x. Okay, well, if we set that one up, we can come up with our 2 functions essentially that we're getting are going to be u of y of u and u of x are the functions that we're considering here. Now, if we want to find out what dy dx is here, the definition is to say, let's take delta x, our small change in x, to 0 for delta y over delta x. Again, remember that delta y and delta x are just our small change away from our original coordinate point xy. So xy is our original coordinate point, and our next coordinate point is x, and this small change in x, which we've been calling h, and y, and our small change in y. Now, obviously, you can actually have a function for this. You put in this into your function, but we're just saying it is a small amount different, given that we are a small amount different in the x direction as well. Okay, so there's our definition, and that's why we're saying it's not a fraction. It is a fraction with a limit on the front. Okay, because we can't actually have delta x being equal to 0. That's the whole problem. Okay, well, laws or properties rather of limits tell us that we can split this up into, or actually let's do, first of all, let's split this, and let's do delta y and delta x here. Now I can split this up because I'm not equaling delta x equal to 0 here. I'm only tending towards it, and this is a fraction. This is not a fraction, this is a definition. This is a fraction. So I can now put in delta u and delta u there. Now, this small change in u is just a thing. Yeah? It could be 0.1, and this is 0.1 as well, and that's definitely going to cancel with this. That's allowed. Properties of limits also allow us to split up those limits. Okay, so we've got delta x tending to 0, and we've got delta y there, delta u, and that's times by limit of delta x tending to 0 of delta u over delta x. And now you can see we have the definition of dy du there times by the definition of du dx. And now we've gone from there to there, which you may think is kind of crazy because, in fact, it looks like we're just cancelling du and du. You can think of it in those terms if you want to. But in fact, this is the proof. We need to go through the algebra of limits because this is defined in terms of limits here. Okay, well, hopefully you enjoyed that one. I mean, you could be asked to prove that. Let's have a look at the other notation here as well. So let's just sort of zoom into this and take this one here. And then let's do that previous example with this notation. Oh, and let's look at what they give us in the formula booklet. Okay, so if we go down here, okay, quite far down, so it's right near the end. In fact, all this differentiation, and so what are they giving? Are they giving us? Oh, the product rule. Yeah, they normally give the product rule, the quotient rule, and the chain rule there as well. So they're giving the chain rule in terms of the fraction style. Okay, and that's actually a change from the old formula booklet. So you can see there where it says chain rule, and it's coming right at the end of all of our list of derivatives, giving this general formula for the chain rule as a product of these two derivatives. And from my point of view, that's the nicer of the two ways of giving it. So this is the alternative way. If they say, look, we've got f of g of x, but instead we're saying, well, we want the derivative of this. So they're definitely, combining those two fractions there and saying, well, this is f of g and dash, but it's also in terms of x. Okay, well, that's going to give us f dash of g of x and g dash of x. Well, let's try that with our function which we had before. So we've got 3x minus 1 squared. Okay, let's just figure out what we've got here. So that's now our f of g of x. That's our main function. And sometimes I like to put that instead. Sometimes they put an O there of, but so we've got 3x minus 1 squared. Now we have to figure out what is g of x. Well, g of x is equal to 3x minus 1. We have to define that. We're saying it's the function inside the function. Okay, and now we can work out g dash of x. So g dash of x is going to give us 3. Now, how do we deal with this? Well, again, here, this is like saying, though we've got f dash of g of x, well, we could equally say that's f dash of g because we are putting in g into our f dash of x, whatever's popping out for g according to the value of x. So really, this is just a value. And of course, by choosing x to be any value in the domain, this is going to give us the range of g of x there as well. But these are just numbers which we're putting in. So we can essentially write this one as, we could just say that this is really f of g is equal to g squared again there. And then we can do f dash g, which is equal to 2g. And of course, g, this function here is in terms of x. So we've got f dash of g of x is equal to 2 lots of g of x. We're just taking that x to make it kind of clear that the x is not timesing by x or anything. It's just the variable that the function is defined in. Okay, so we've got two lots of g of x, and g of x is actually two lots of 3x minus 1. Now that gives us 6x minus 2. And now when we times these two things together, you can see that we can get 6x minus 2 times by 3. And we're going to get the same as before. So, I mean, another way of thinking of that is just, well, forget about the g of x. If it's saying f dash of x, all it's saying is take the 2 to the front, reduce the power by 1, and forget about, and then times by the derivative of what's inside. That's another way of considering this. Okay, so another way of dealing with this would just be to say, well, look, here's our original function. This is our f dash of g of x. Well, so now bring the 2 in front, reduce the power by 1, and times by its derivative, the derivative of the thing which is on the inside. Okay, right, well, let's have a look at the questions from the book. So we've got example 19. Let's just zoom down a bit here, okay. So got example 19 here, so it says differentiate 2 minus x 11x all to the power of 10 WRT x with respect to x. So what they want is dy dx, that's what we're looking for. But let's just define to start off with our u. So we're saying that y is equal to u to the power of 10, and u is equal to 2 minus 11x. So dy du equals 10 u to the 9, du dx is going to give us minus 11. And now when we times those two things together, we can get dy dx equal to dy x, split it up, du there. dy du is 10 u to the 9, and then that's going to be timesing by minus 11. So we're getting minus 110, and obviously we need to put u back in. So we're getting 2 minus 11x, and that's the power of 9 there, don't forget that. Okay, now obviously multiplying this out using a binomial expansion would be pretty hellish, and then differentiating each of those terms. So fantastic that we've got the chain rule now. Okay, so there's that one. Let's just have a look at that. Same. Okay, now example 20 before the exercise. So, and we're cracking through this pretty quickly. Example 20, differentiate this function here. So let's just write it to start off with in Indices Notation, which is often easier when we're talking about differentiation. So we've got this, and now we can say we've got y equals u to the power of a half. U is equal to 4 minus 3x squared. The u dx is equal to, there's no gradient from the 4, from the constant, so we're just getting the minus 6x there. And when we differentiate this one, we get y u is equal to times by a half and reduce our power by 1. Okay, now we might want to write that as 1 over 2u to the power of a half there, or square root of u. That's the same thing. If this is saying both take the square root and take the reciprocal as well. So let's then times those together. So we get dy dx is equal to, I'm just going to write 1 over 2u to the half there, times by minus 6x. Putting that in, and I'm putting that in. Okay, when we times those two things together, we can see that we're getting minus 3x. So 6, the 2 is cancelling to us 3 on the numerator. It's like minus 6 over 6x over 1. Got the x on the numerator there as well. And now we just need to put this thing on our denominator. So we've got 4 minus 3x squared square rooted on the denominator. Now that's the same as if we put this on the numerator to the power of minus a half. Same thing. Okay, that's just laws of indices. Okay, well, let's have a little look at that one. And there we go. You can see that they've written it in this radical form here. So in the square root form, to be consistent with the question. You should really be consistent with the question at the end. If you are being asked a question with square roots in, then you should leave your answer with square root signs in as well. Okay then, guys. Well, there you go. That's that. There's 4i coming up. There's 7 questions there. And next time, we're moving on to, I would expect, the product rule and the quotient rule. Yeah, we've got a product rule coming up next as well. Okay, so thanks for listening. Hope that was useful, and hopefully see you back next time.